Let's try to look at another important aspect in networks called the network telemetry. This is about getting the visibility of what's going on in the networks. And this has been a significant pain point for network operators for several years. This is primarily due to the lack of necessary tools, the means to look at what's the aspects that's going on in the network and what's the real-time statistics at each of the networking devices. All of these have been really challenging, and it made debugging the networks and troubleshooting in case of any issues a very hard task. And this is where we need to relook and see what can be done better as we spoke about the network softwareization aspects and carry forward into this aspect of network telemetry. And this is all about measuring the networks effectively so that we are able to collect the data. But beware, like we spoke about the several gigabits links, and even when we considered just the 10 gigabits links, we are talking about millions of packets per second. And now with hundreds and 400 gigabit links, this will be multifold. So anything that we want to define or provide the mechanisms should be able to scale and be able to operate at such a very high traffic loads. And that becomes an important aspect as well. And how we define network telemetry is basically a technology through which we can gain the insights into the network and facilitate for efficient management. And in this context, several of the works were put forward in over the last few years. And the one that came from the IETF, which was very recently published in May 2022, is this IETF RFC 9232 that is bringing and defining or charting out what the network telemetry framework should be so that we are able to do these tasks efficiently. And the other series that happened with the network softwareization group of what we looked at before and how we tried to go towards the programmable networks is this in-band network telemetry for data plane network analysis. And we'll try to look into INT and also see how this has resonated into the network telemetry frameworks in specific aspects. Primarily, to just think of the background, if we had a topology as shown here, a very simple one with several of the routers for just between the two end hosts where the network would be exchanging information. Now, the important aspects that we would want to consider when any of the packets that get lost in the network is to know where exactly or which router in the path did it get dropped. And if we are seeing for a latency sensitive flows that we are missing the deadline, we also want to know at which router in this topology resulted in having a lot of queuing delay or which contributed towards the majority of the delay which made the deadlines to be missed. And if they were throughput sensitive, we want to know which of the links are currently constrained or over-utilizing the bandwidth and affecting the flow's throughput. So all of these questions that will come when we look at such a simple topology. And even to the very basics, when the packets go from source to the destination, we would want to know what exactly happened to that packet. And we can see when we spoke of data center networks, there are a lot of paths through which the packets would flow. So it would also be important to know which paths did the packets traverse in the first place, because there may be lots of packets that may be traversing as through different paths in the network. So, and as they traverse, we would also want to know exactly the list of the switches and routers that they visited to eventually make it to the destination. So that means they should be able to provide us saying the packets visited basically switch 1 at a particular time, and then going from switch 1 to switch 2, they visited and left the switch 2 at a particular time instance and eventually made their way out to the end host. And likewise, when we see the packets to flow through these different devices, we also want to know, like, if a switch 1, as it visited, what kind of rules were applied to it in terms of the way that forward out on port X, port Y, port Z, or maybe do some processing on the headers, like we say the NAT, whatever the translations that we may be doing. So all of these information in terms of any transformations or any rules that each of these devices applied would be an important aspect also to look at, to say that as the packets went through this router 1, they were applied with a specific rule to say the match on 192.168.0.28 before with the match rule, where they would process certain actions. So what kind of actions, how many actions were applied at each of the switches as the packets traverse through them would be an important aspect, because many a times if we have a properly configured NAT or a firewall rule, we may not have the connections to get established, and it may be very hard to debug the issues where at those particular devices where the firewalls were dropping the packets, where the NATs had improperly configured the headers and not making the packets to go through. So there can be various of these aspects that we would also learn if we knew what rules were applied at each of these switches and routers. And likewise, as the packets traverse, we would want to know at each of the switch or a router, how much time did they get enqueued? Because if we are seeing latency sensitive flows, we would want to know which of the routers or switches contributed towards the majority of the latency and for what reasons. So if we are able to extract information as saying, I encountered the delays of 100 nanosecond, 200 nanoseconds, and like this 19740 nanoseconds at each of the routers, then we can very easily pinpoint and say that the main concern seems to be in the router 3, where it is experiencing abnormally high delay. And likewise, we would be able to know, if we are able to capture this information for every packet in the flow, we would be able to see over time how the queues have built up at each of the routers, what's going on within each of the routers in a very fine-grained manner. And this would also help us to know, okay, yes, there is a latency that has been spiked at this router 3, but this could be due to some other externalities, and we would want to know what kind of externalities caused this kind of an effect. And in a sense, that would mean that maybe at the time when this packet was reaching the router 3 and having the packet go through this router, maybe there were other flows that were hogging the bandwidth, and maybe they would have occupied the queue, and because of which the green packet ends up having to be queued for a long time, suffering abnormally high delay. So there can be several of the aggressor flows that may be flowing through the switch at the same time. So you would want to know if the packets shared the queue with what all kinds of the flows at a particular device. So if we have such an information, then we would be able to make the deduction that the green packets led to very high delay or latency queuing delay. That's because it is this router 3 was occupied with lots of packets from this orange path or orange packets, and these were the concerns for seeing this abnormal high delay. So in a sense, when we want to build this network telemetry framework, we would want to understand and answer all of these questions, like which path did my packet take, which rules did my packet follow, and at each of the switch, how much did they spend time in getting queued before getting processed. And if they were queued long enough, we would also want to know with whom all did they share the queues while they were residing at the queue at a given router. So answering all these questions was in effect the goal for us to do better network telemetry. And this is where the P4 group tried to come up with this in-band network telemetry, which would try to answer all of these questions. And most important part here is not just to answer these questions, but also to ensure that you are able to do that without impacting the packet processing at a line rate. That means we should be able to do that for several million packets per second in a non-intrusive manner. Or it could be a means where we could develop mechanisms which can allow us to do that in a very least overhead fashion. And it is also important that if we have per packet details, we don't want to be generating extra packets into the network adding to the bandwidth tax. We also want to minimize this bandwidth tax that we would pay for just collecting this information. So think of, if I have 1 million packets, I add 1 more million packets, making overall 2 million packets to be traversed to get this information. That would be infeasible. So we would want some intelligent and nice mechanisms that would allow us to have this done in a very low overhead fashion. In a nutshell, in-band telemetry tries to leverage the mechanism where as the packets traverse through each of the switches and routers, the switches and routers, which we now consider to be P4 programmable, would be able to look what's the current characteristics and the status of each of these devices and add the information into the packet header as the packets traverse for the required details that we want to collect and log at each of these routers. So as the packet reaches the router 1 would then stamp the details in terms of what is the switch ID, what was the arrival time of the packet, how much time did that packet spend at the queue within that switch, and what were the matched rules on this particular switch. All of these informations can be padded onto the packet and then forwarded it onto the next router. And as it reaches the next router, again, the next router would do the same, adding its set of informations similarly and appending it to the packet. And likewise, as the packet traverses through the set of switches and routers, we'll see that each of those routers would append their end of the information. And as it reaches the last hop router, the last hop router can take out this information and provide these specific details that were collected as the packet traversed through this network to provide for further logging and analysis of the details while sending the original packet to the end host as desired. So in essence, we make the information to be made available in band within the packet as the packet flows through the network, and extract out the information at the last hop and ensure that the packets that are delivered to the end host are the same as what the source transmitted. So let us try to understand briefly about how the INT evolved and what are the key modes of operation that INT brings forth for the network telemetry. So the early work started in around 2014 with the paper Millions of Little Minions in SIGCOMM 2014, which was followed up by in-band network telemetry via programmable data planes as a demo paper in this SIGCOMM 2015. This originated the idea of how in-band network telemetry can be used and the development of a framework that would allow for collection and reporting of the network state in real time at the data plane without requiring any of the interventions or the need for the control plane as such. And this work initially resulted in the culmination of an initial INT spec in the early 2015, and it started taking to shape with respect to saying what should be the means to facilitate this INT information, where in the packet header, if the information has to be embedded, what should that be, and what kind of information that need to be extracted, and what are the means to specify which information needs to be extracted at a switch and where to embed. All of these started to take shape, and a P4 applications working group was formed in 2017 to bring about the exact means of making these prototypes to work. And this led eventually to the formation of the version 1.0 of the INT spec, with the development were led primarily from the Barefoot, which were the pioneers in the P4, and several other board members started to join and operate in building towards this INT v1.0 spec. And this evolved over the recent years, and there have been various adoptions that have been done from Cisco, Arista, Xilinx, Intel, ONF. All of these people have played a crucial role in paving towards the newer variants of the spec, and the most latest version is this INT v2.1, which is the current version of the spec, which defines specifically what are the domain-specific instructions that a switch or a router should be operating, and what are the modes of operation that INT should be facilitating, and if this information has to be embedded within the packets and sent, what is the means to tunnel the header so that the original information is not affected, while the switches should be able to understand the INT instructions and do specific processing. So all of these details have been laid out in this INT v2.1 spec. And in the brief time, let us try to understand some aspects of how this INT processing happens and what we mean by different modes of operations, what are the key tenets and principles on which the INT designs were considered and laid out. So the key development principles were primarily to leverage P4, the programmable data plane aspects, so that the switches and routers could embed and look for necessary information, add that data, extract that data in a defined manner. And because now we are seeing the programmable data plane, it also gives us the flexibility to define the header formats the way we would want, so that the main insight here is to ensure that we are not confined to any specific protocol version or a packet types. We could be generic enough to facilitate any of the data types. And because it is now programmable, that also means that we will have the software development at a very high velocity. So the key development principle also involved to say that the hosts have to be agnostic to the INT information that would be generated underneath in the network, so that the endpoints need not have to worry about how this information is being added, how this information is being collected and analyzed, and work as if there is no change. And in terms of the network, when these switches and routers that would want to append and add operate on this information, they have to be flexible in terms of what kind of an operational mode they would want to work, where the data would come. Because we have seen that if there were IPv4, IPv6 routers, you have a tunnel. And if there is a LAN and you have the VLAN headers, VXLAN headers, so all different kinds of tunnels, different kinds of packets would flow in the network. So we don't want to be binding to any specific protocol headers for this INT information. And INT should be facilitated over either the TCP or UDP flows with the VXLAN or a Geneva encapsulation or IPv4 GRE. All of these, regardless of what kind of a encapsulation or a packets they are, we should be able to facilitate supporting INT. And this also means that as the packets would want to process them and add the information, the instructions that define what kind of operation or what kind of data that the switches need to add should also be having specific instructions. And we want to basically define domain-specific instructions and at the same time make sure that they are flexible enough so that they can be expanded for the needs that the network operators would have. And in terms of reporting the information and what model you would want in terms of facilitating the data to go through different switches and update to the monitors, we would also want to have flexibility there in terms of what can be supported. To say that we want to have a mechanism where the network packets can be processed independently, and each packet should also have this metadata semantics which tells what kind of an information is embedded within each packet, and so that it can be processed independently and sent for the log analysis. And here it tries to take advantage of a YANC data modeling, which is basically the modeling which defines the hierarchical data structures that can be used for operations based on the network configuration management or the netconf. And these provide the tools for the network administrator to enable automation of the configuration across heterogeneous devices. And INT tries to leverage the same concepts in trying to deliver the network data. And if we look at what this INT then consists of, it's basically three key aspects. One, if we want to monitor, we should be able to identify the traffic that we would want to monitor. And in this sense, what the INT specifications define is a watch list. And this watch list consists of the kinds of flows that we would want to monitor, that is, to specify the set of flow spaces which are of interest for which we would want to collect certain data. And when you want to collect certain data, you would also want to say what kind of instructions that you would want to apply. Like, do I want to collect the delay parameters? Do I want to collect the queuing parameters? All of these informations should be that we want to collect should also be able to be defined. And in this essence, the watch list tells basically the flow space, which could be IP5 tuple or any additional packet header fields, not just confined to the 5 tuple if we want to match. And once we have defined the watch list and what kind of an operation that we want to do, the second important thing is to also say what kind of match, once you have a match, what kind of events that you would want to generate or trigger that you would want to set so that the logs can enable you to look out for specific actions. For example, dropping of a packet is a kind of an event. Or if you see that certain packet from a particular source IP on a source destination port is coming, that's a kind of an event. So we should have the mechanisms to say what kind of events are generated because of these packets, which we can, again, through P4, we can program the switch to say when certain conditions are met and what to do when such conditions are met. And this is where the intelligent filtering component comes in to say that you want to be looking out for the flow events. And if you are talking of just the TCP, whenever the TCP flow starts, like with a SYN flag, that's a very simple example to say that, okay, we start to see a new TCP flow at this point, or when we have the TCP flow terminate with FIN. FINAC flags, then we can also mark these as special events. Or even if we want to have any per flow statistics that on a routing path that we want to look for, or a packet drops or a queue congestion, all of these basically become the triggers on which we would want to set. That means we need a mechanism from the INTs to say how to watch out for these as a key instructions, and let the switches or routers look out for these and process them. So the means of program that would do this, and the instructions that would specify what program needs to be run on a switch. And once we collect all this information, we need a means to report to a certain entity, and the means to formulate the report and send it to an agent. And all of these aspects are the core tenets of INT. Let's try to cover some of the INT modes in terms of how the operations are being defined and what informations are being prepared at each of the switches and how the information gets logged onto the monitors. So the INT comes with various modes of operation, and one of the very simple modes is the INT embed data or INT MD mode. And the construct here is to say that as we have the packets go from the one host to the other end host, they would traverse through different switches, and for each of the switches we would configure the watch list. And once the packet flow space matches within that watch list, then a certain kind of actions that need to be taken as instructions and specific data associated with those instructions would then be padded for each of these flows. So to think of as the host 1, which is agnostic to the existence of this INT, would send the header and payload information to make sure that data reaches to the host 2. And as it reaches the switch A would look up in its watch list and identify whether this header matches any of the entries in the watch list. And if there is a match, and it would then pad what are the corresponding instructions that it needs to follow in terms of what we want to monitor, what are the events that we are looking out for this specific kind of a packet, and then add that information in terms of saying, now we want to have these packets to be processed with these kind of instructions. And for these current instructions, what is the information that you have at a switch A? So that gets padded as basically the INT instruction header and the info switch A, which actually processed this information and padded. And in this terminology, switch A is basically the ingress switch at which the INT monitoring starts. And any subsequent switch that the packets would then go through will basically look at this INT instruction header within the packet and then start processing and updating the information. So any subsequent switches that you would see are what we call as the INT transit switches, while the first switch where this information gets added is what we call as the INT encapsulator or the ingress switch. And the last switch where this information would be taken out is called INT decapsulator or the egress switch. So as we see that the packet goes through the switch B would look up this INT instructions and add its kind of information, maybe the delay if we are trying to monitor, or what kind of flows were in the queue at the given point as this packet progressed. All of that info would then be padded onto this packet and forwarded further, even including if we are monitoring for the kind of rules that were applied at each of the switches. All of this info would be written out in this switch B info and then forwarded over to the switch C. And as it reaches the switch C would also add its information with respect to whatever the INT instructions were specified. But before forwarding the packet onto the host 2, it would decapsulate this INT information, extract it out, and then just transmit the header and payload information to the host 2, while sending the entire INT information that is collected as a part of INT instructions, switch A info, switch B info, and switch C's own info. All of this gets padded and sent out to the monitor. So this is a very native means to say that we are able to generate the INT information within the packet itself, and that's why it's called the embed data mode. And with this model, the information would be extracted out at the last egress switch and sent to the monitor, while the packets between the end hosts go as plain. In this model, what we see now is that the information that is being added for the INT makes the packet to bloat as it traverses multiple of the switches. And here, it could be possible that the packets that need to be fragmented due to the link constraints that you may have in terms of the MTU may have some concerns. Nonetheless, this is a very classic, simple format in which we are able to monitor within the packet. And here, the switch A, which has the watch list, is what we call as the ingress or the int source, and switch C, which is the last switch that processes this INT, is called as a int decap or the sync switch that basically takes off this INT information. And note that when we have lots of switches and lot of information that gets padded, it may become difficult to fit within the MTU size. And also the other thing to look at is that as the packet progresses, we are increasing the size of the packet that flows through each of the switch. So that means the bandwidth constraints could start to increase if we have loads of switches through which the network has to pass through. And here we also have to be cautious about what kind of information we can embed and how efficiently we can embed so that the headers are all, the information that we pad is minimal. And the next kind of a model is what we call as the export data model. And here the information that used to be padded at the source and then the one that used to be padded at each of these individual switches and then sent back to the sink, we can try to view it in another model, wherein if each of these switches have the information configured, they can do different kinds of event detections altogether. Maybe I need certain kind of an information at switch A while I would need certain other kinds of information at switch B. Then I want the configuration flexibility to define what gets matched at A through a distinct watch list and what gets matched at B through a distinct watch list. And for the same flow space, I may have different instructions for switch A, switch B, switch C, and likewise. While in the earlier case, we saw that the packet would have the INT instruction which specifies exactly the domain-specific details that each switch have to carry. Here, we are making much more flexible to say that each switch may have their own domain-specific instructions for a given flow space, and this way we can have the collective information that can be collected across different devices. So the mode of operation is like once the packets are sent to the first source switch, whichever the switch that sees the flow space of a host 1 packet to match in its watch list, what it would then do is generate the INT packet separately and based on whatever the watch list rules that have been configured. Like if switch A was asked to report the kind of flow rules that it matched at this particular switch, consider this is an ACK, then we would want to know what kind of a flow rule, which index did it match, what were the changes that it did, and the switch A would then accordingly prepare for each of these packets that it matches into the packet header and information taken as a separate INT packet. And then the switch A would send this information to the monitor at the point that it processes this packet and forward the packet as it is to the switch B. So you can notice now that there is no extra information that is padded to this packet. So there is no INT header, the domain-specific instructions, nor the data that is being padded. So the packet goes as it is. And likewise, when the switch B sees this information, and if it has its own watch list where this header matches, and it might have its own kind of information that it wants to extract. Like considering this is a core switch at which the informations are flowing, we would want to know with what other flows that this switch packets are competing with. And we may want to extract this specific information and the delay information at this switch so that switch B can add whatever the information that it wants to add and craft out a separate INT packet and send it to the monitor while sending the original packet towards its destination as it is. And likewise, again at the switch C, it may have its own watch list. And if it were typically a sync, we would want to know what is the total delay that it might have observed as it is coming or any other metrics that we'd want to look for and extract that kind of an information and send it to the monitor for the same packet and then send the packet to the host 2. So in this model, we have basically ensured that the packets are sent as it is across the path. And 2, we have provided the flexibility to say that different switches can operate with different watch lists. Note what that means is if switch B had a watch list that didn't have any match for this header, switch B would not be sending any information towards the monitor. So we have given this flexibility now to say that we want specific points in the network where we want to observe for certain characteristics. That can be done through this watch list configuration at each of the switches. And further, we are making sure that the information goes in the off-band manner for the INT towards the monitor. So each of the switches would be configured with a monitor where they would want to send. And it is likely that we may not have just one monitor. We may also want to build this monitor at different points, which is more flexible and convenient to collect different kinds of informations. So the monitor, think of it as an aggregator, and set of aggregators. One may want to look up for latency, one may want to look up for the rules. All of these informations can be spread, and not necessary that you want to do all of them at once. So that's the flexibility, this int export data or a postcard method, where the information of INT is embedded as a specific packet as a postcard and sent towards the monitor. This, in a way, we can see that it complements what we saw earlier with the int embed data format, where the data was flowing in band. Here, the INT information that is collected is in a way flowing at each switch, although in band with respect to how the packets are going to be processed at each switch, but the information itself is sent out of band in a separate postcards. The alternative way to see it, if we consider way that we just saw, you had to maintain the watch list at each of the switches. And when we say of watch list, we are speaking of millions of flows for which we want to keep this information. And this can be costly at times to maintain it at each of the switches. So the means of now to rethink, if we had the watch list just at the host where we have abundant memory, and it would then see what packets before it is trying to send out to say what instructions for each of the switches to do. And then you would want the switches not to keep any memory for watch list, or not to do, because this also means that you have to match and then do some processing. We want to eliminate those overheads in terms of processing cycles and memory overheads. We can do that as well, push it to the hosts, or even it could be not just the host, but it could also be one of the switches to say as an ingress switch, the first one where we could add this watch list. And once that is done, what that will follow is to say that you have an domain-specific instructions that are added for a particular packet, and as the packet traverses through different switches, you would want to detect just the events rather than looking up for the watch list in a specific memory and then match the instructions. You would look up the instructions right within the packet, take necessary actions to do the processing and generate the events out. So let's see how this in fact operates. So as the packets move through the host 1, it would generate the watch list, send the information. At the same time, it would pad this INT instruction header. Now this information is sufficient for subsequent of the switches to look up and generate their packet headers. So likewise to the postcard method, you can see that each of the switches would then send their part of the information towards the monitor. But what to process on, they need not have to keep a specific watch list, but can take the cues from the INT instruction that is padded in the header and do the specific processing and send the information towards the monitor. And eventually the packet reaches with just as it was sent out from the host 1 with header, INT instruction and payload, and then INT instruction can be consumed at the host 2 and then sent with just the header and payload information. So this embed instruction model helps to say that we have a uniformity in terms of what each switch would operate on in terms of the instructions, and the information that is being collected by each of the switch for each different packets is being sent in band with respect to the packet processing towards the respective monitors. So it, in a way, combines the best of both the worlds. And we could also have a means where we could say, okay, why just have the in-band instruction? At times, we would want the switches at the subsequent hops to know what happened before. And if they need to have that intelligence, we need specific source data. Consider when we spoke about the delay, where you are having a certain delay budget and you want to work on within the delay budget. Then I have to know what was the exact delay that it incurred at the prior hop so that I can do the processing in a different manner. So having not just instruction but also specific data could help the subsequent downstream switches to operate in a better manner, and also ensure that if there is some information that you would want at each of the ends to process, this would help to say that I can add minimal information in the in-band model of the packet as instruction and data, and any other information that we would want to collect as a postcard model could also be sent. So this is equivalent to saying we have the embed instruction with source data that we could pad at each of the switches, but confined to a subset of memory that we would want the packet headers to bloat up to. Overall, with these modes of operations that we discussed, INT opens up for a very nice mechanism for fine-grained visibility and generation of the key events that would help us react much more quickly and have good troubleshooting aspects. So it opens up for very simplified means to troubleshoot the network issues, wherein we can generate and add the INT instructions to meet what kind of characteristics we are looking, aspects that we want the switches to append and add. Because it is programmable, we can even add any new sorts of information or programs so that the switches could add this information very readily. And second, we saw about the congestion as an important aspect that we want to meet in a sub-microsecond time scales. And if we have to do that and we want to utilize the parts of the network in a much more better fashion, we want this intelligent path selection to base on the information that we gather in real time. And this is possible with INT now to check for which of the paths are having what congestion levels, or where the queue is building up, where the queues are low, and accordingly make the decisions of routing the packets. And there have been several works that have come, like Hula, that try to use basically this information within the networks and do better optimal path or optimal routing. And likewise with respect to congestion control and network management and overall capacity planning, all of these can now be done much more easily. So this would also mean that the expenses that we would have to do on the operations of the network would also be lowered, because now we are able to do it in automatic fashion, where the monitors that are going to be run as programs would be working in the background without needing much of the overheads from the network operators. So all of these in a way greatly simplify the network operator's life and also enable to provide rich visibility of what's happening in the network, and to add what we can call as the automation for course corrections or updates that we want to build on the network through the use of INT. Let's try to look at just a couple of use cases in terms of how this INT has been very useful. So if we consider like a case where the packets get dropped in a network and we don't know where exactly are the packets that are getting dropped, or we know that okay, the packets were dropped at a particular switch, but for what reasons were they dropped is not sure, because they may be dropped due to the corruption of the packet headers, which the packet is not able to be read and be processed, or it could be that the packets are dropped because you have the queue full, or it was that there is a rule that was configured to say that this packet needs to be dropped, or you got a packet which was not having any matching rule and you don't have any means to process that packet further. So if we want to understand what are all the aspects that could be happening with a given flow packet, for what purposes it was dropped and how it was being done, and if we consider at a switch, the most common would be where you have a queue where the queue is building up and you want to know if the queue overflow happened or because you had a write configured and you are doing the drop early on this particular packet. So there may be different reasons why this packets could be dropped. So if we see any such packets, if they are dropped, we would want to understand precisely the reason and what triggered for this packet drop. And if we are able to configure a drop watch list into a switch, and then whenever a packets that go through, and if they were monitoring for these packets, for if they set the rule of the headers in the drop watch list, and if such a packet becomes a victim which is going to be dropped for either of the reasons we discussed, then information can be triggered out from the switch and sent to the monitor to report exactly the reason why the packets were dropped. And this would enable the network operator to understand what's going on and what's the reason and behavior and take the course corrective measures. And likewise, if we have a use case where you want to watch on the queue size, and if the queue size is indicative of congestion when it exceeds certain length, we want to build this information and report back to the monitor. And that way, if the packet headers match it to be in the queue watch list and see that, okay, there is a packet that is being queued for this duration, and then the information about the queue congestion can be reported back to the monitor with appropriate reasons of how much queue and in terms of what all packets accounted for that queuing at a particular switch. All of this information can be padded in the packet header and sent towards the monitor. And then this way, the network operators can again look that maybe this time there were these flows that were competing and which resulted in this queuing. And what is exactly the queuing behavior, the way it is happening over course of time can also be monitored thoroughly. See, now if we want to retrofit and think about how we learned about the DC-TCP, the way it operates on the incast, is there a way that INT can have an impact over there? And there was a demonstration that was done which said, let's try to see how the incast happens and where this INT can really help. And what we saw, if you recollect earlier, what we said, whenever multiple of the flows are being sent towards the destination top of the rack switch, or basically we called them as where the aggregators would see a lot of information from the worker nodes. And the worker nodes are basically a lot of these at the top of the rack, which are now going to send the information towards the aggregator. And aggregator is again somewhere in other side of the top of the rack in a data center, towards which all of the other workers were trying to send the info packets. And this all happens in a very small microseconds time scale, and we will end up seeing a queue buildup at the aggregator switch or the destination top of the rack switch. And this resulted in what we called as a TCP incast, and packets would be dropped at this switch because of not having sufficient buffers for that microburst. And the way we said we would react is basically we mark the packets as we forward them, whatever are the packets at that instance, and send it, and then send the receiver to send an acknowledgement back indicating the senders to slow down or change their means of their sending behavior. And also in DC-TCP, we said it's going to be multi-bit information that these senders would take into account and then adjust their rates accordingly. But one important observation that we have to make is such a thing to operate requires one round trip time. The time the congestion occurs, the information will go back to the sender only after the receiver has sent an ACK back with the CN. And sender has to wait for one round trip to say how to react, because he has to collect all the CN bits, aggregate them, and say how much was the congestion perceived, and then adapt the congestion window accordingly. So if this can be bettered and if we can leverage INT, what we can think of is to say that at the ingress, as the information is of the TCP incast and pursued congestion builds up, we can basically notify back directly as the packet info with the INT packet info as a signal coming towards those particular senders at a time, so that all the senders who are contributing towards the TCP incast or a microburst that's resulting in a congestion can all be notified upfront and make sure that this information reaches the sender much earlier. And this information can precisely cover what exactly has happened over a window of time within this ingress switch, and you don't need the senders to collect again and wait for RTT to do or take certain actions. And that way, the information can be sent back in a much faster manner. And at the same time, once these switches receive this, they can apply either the source flow control or the priority flow control means to notify the sender, and sender can react back to say how they can react and slow down their sending rates. And at the same time, as we did earlier with respect to how the congestion notifications were sent, the ECN marking can still be followed and sent towards the receiver, and the receiver can then basically take this congestion notification signal and send the acknowledgement back to the sender. And the sender can also have the traditional means of reaction that you would be doing. And overall, now we have built a scheme where we are able to react much more faster in a much more fine-grained time scales than waiting for the entire round-trip time, and also leverage on the mechanisms to say how the senders should be able to react using either the SFC or PFC schemes between the source top of the rack switches and the sender, and make this solution that can address the TCP incast problem. And this is also termed as back to sender, or the BTS source flow control scheme in IEEE. And to summarize, if we see now with the SDN world of what we started our discussions, at the data plane, we can have the in-band network telemetry that can help monitor all the characteristics at each of the network elements. And this information can be collected and observed for any anomalies or any aspects that we would want to build analytics, and pass it up to the control plane. And the control plane as well can monitor this kind of a state, validate in terms of what is the behavior, and adapt its operations according to the monitored details that we collect from the INT. And this further can assist in enabling the pattern of how this control state changes are going to be impacted through the network management and operations, so that now we have a fine-grained control over the entire visibility of what's happening at the data plane, helping the control plane to make better decisions, and also the management plane in terms of the control applications to say what you want to run, what kind of information you would want to build, and all of this end-to-end observations can be built up. And this is where the other work that I mentioned from the IETF, the recent operations and management working groups specification in terms of IETF RFC 9232, which came just in around May 2022, speaks about the applications of network telemetry at different planes, not just at the data plane like what the INT does, also applied at the control and management plane to ensure that you are able to build a framework that is holistic enough to get the informations at each of the levels. For more details, you would want to look at this IETF RFC 9232. But what we have covered is basic aspects of how the INT operates, what are its use cases, the operational modes, and the benefits that it brings to the table